Today, we'll be working on the Robinson Annulation reaction, which is a multi-step reaction, first following a Michael addition, then an aldol reaction, and then an aldol condensation reaction. For this reaction, we are going to start with a cyclic dicarbonyl compound. This means that we have two carbonyl functional groups, which suggests that we have 3 alpha carbons. 2 of these alpha carbons are symmetrical, and we will label these in green. Now, there is a third alpha carbon that is unique, which we will label in red. Now, how do we decide which alpha carbon to deprotonate? In order to decide this, we have to look at the pKa's of the alpha hydrogens. The alpha hydrogens attached to the green carbons have a pKa of approximately 20. Now, the pKa of the alpha hydrogens attached to the red carbon is approximately 10. This may not seem like that large of a difference, but because pKa is measured on a logarithmic scale, the difference is actually 10 to the 10. So because the hydrogens on the carbon in between the carbonyl functional groups is significantly more acidic than the other alpha carbon hydrogens, this means that this is going to be the carbon that gets deprotonated. So now that we've decided which of our carbons is going to be deprotonated, we need to talk a little bit about the Michael reaction, which is the first reaction in the Robinson Annulation reaction. In the Michael reaction, we have a Michael donor, which is going to be our cyclic dicarbonyl compound, and a Michael acceptor. The Michael acceptor will have an alpha-beta unsaturated bond, which means that the alpha carbon and the beta carbon have a double bond, which suggests that they each lack 1 hydrogen. So to start our reaction, we are going to deprotonate the carbon on our Michael donor. So we'll use a general OH base for this, and that OH will grab a hydrogen, and the hydrogen's electrons will move onto the carbon. The electrons of the negative carbon will attack the beta carbon of the Michael acceptor, moving the double bond to the middle bond and flipping the double bond electrons up onto the oxygen. We have now formed the new bond between our 2 compounds. That being said, the negative oxygen species is not particularly stable, so there will be a step where we tautomerize. In this tautomerization step, the electrons from the negative oxygen species will flip back down to form the double bond. Because the carbonyl carbon now has 5 bonds, which a carbon cannot have, this will push the double bond to grab a hydrogen in order to resaturate the alpha carbon. This is the final step in the Michael reaction.
Now we will be moving to the aldol reaction. In this reaction, we have 2 options for alpha carbons that we can deprotonate. We will be choosing the red alpha carbon due to the fact that when it is deprotonated and reacts with the other ring, it will create a stable 6-membered ring. With the deprotonation of this carbon, we create a carbon nucleophile. This carbon nucleophile will attack one of the carbonyl functional groups on the ring via an intermolecular reaction. This intermolecular reaction will form a second cyclic structure. The carbonyl pi electrons of the attacked carbonyl flip up, forming a negative oxygen. Next, we finish the aldol reaction step of the Robinson annulation with a quenching step, using H2O in the solution. We will quench the negative oxygen formed in the intermolecular reaction previously. Next, we move into the aldol condensation reaction, the last step of the Robinson annulation. This reaction is an E1 carbanion reaction. For this step, we will want to form a double bond between the alpha and beta carbons of a carbonyl functional group. We have 2 options for carbons in this structure to deprotonate to form an alpha-beta double bond. We have the carbon used in the aldol reaction step previously, marked now in green, and the alpha carbon of the original ring, marked in red. Due to the carbon in red being more substituted, this carbon will be favored in the formation of the alpha-beta double bond. We will use another OH group in solution to deprotonate the more substituted alpha carbon. This will cause the electrons to flip down, forming a negative charge on the carbon, like so. The electrons move down to form the alpha-beta double bond. With the double bond formation, the OH leaving group is kicked off. This concludes the aldol condensation reaction and gives us our Robinson annulation product. Now that we have our Robinson annulation product, we can check to make sure we've done everything correctly. First, we want to make sure we have an alpha-beta double bond. Second, we want to make sure we have 2 cyclic structures. And third, we want to make sure we have a carbonyl functional group on each of the cyclic structures.
Now that you've checked for these 3 things, you have your Robinson Annulation product, and probably just a few tissues saturated with your own tears. Good job!